Yeah, any questions before we begin? So we're pressed on time. So we have 3 lectures for Module 5, which we start today. Your Module 5 exam is next Wednesday. And then your final exam, I believe, is the following Wednesday. Either Monday or Wednesday, I'll have to verify that. But the time for that final starts at 10:45 a.m. and you have until 12:35 p.m. So you don't get the entire time that the university allots, because the final is written by the American Chemical Society and you get 110 minutes for that. So that's 70 questions, choices A, B, C, and D. Kind of looks like the exams you've taken that I've written. You have to be in person to take that. You have to take it. There's an actual university policy. I can put that on Canvas if you want to see it. So you have to take that final. If you don't take it, please read the syllabus about the policy for what happens then. So you can calculate your grade. Probably do that next week, Thursday sometime, using the Excel file I created to see what your letter grade is. It's possible you can go into the final with an A. If you tank the final, you still get an A. So your points earned are your points. But if you're looking to elevate your grade, then you'll have to perform accordingly on the final exam. Any questions on that? Okay, so as we start Module 5, we're going to look at a couple different mechanisms. The main one is called the elimination. So E1 or E2. Again, the number stands for the kinetics related to the mechanism. So 2 is bimolecular, 1 is unimolecular. And elimination reactions in general, for the last 3 lectures here, and if you go into Organic 2, elimination reactions form pi bonds. So where have you seen pi bonds before? They're in alkenes, they're in alkynes, and they're in carbonyl groups. So we're primarily focused on the formation of alkenes for the remainder of the semester here. So once we learn how to make them, then we're going to add things back to them. So we make alkenes, and then we do addition reactions. So Monday and Wednesday of next week are going to be pretty busy with a lot of different reaction conditions. But the take-home theme of that is you have a pi bond, so a carbon-carbon pi bond, and then you're going to add things to that pi bond. And we'll look at the different mechanisms by which that occurs. So up until this point, we've seen how these constituents from petroleum, hydrocarbons, we can do CH substitution through a radical mechanism. We get a halogen in the molecule. We can then substitute that halogen either through SN2 or SN1. That introduces different functional groups, and then we know of spectroscopic ways to identify those functional groups. So now what we're going to do once we have that halogen in is we're going to eliminate it to make an alkene. And then from the alkene, we sprout off into all these different directions to make addition products. So at this point, we really want to understand nucleophilicity versus basicity. So nucleophilicity is the rate of attack on an electrophilic carbon. So that's, you have a nucleophile and it's substituting for a leaving group. So you're forming some atom to a carbon bond. Basicity is the action of abstracting a proton. So what is now more complicated about the bimolecular processes, which we'll start with, you have to look at the nature of the reagents employed. Is it going to act as a nucleophile to do a substitution, or is it going to act as a base to do an elimination? So in blue here, with the blue reaction arrows, we've seen SN2 already. So the nucleophile, which is the Lewis base, that's supplying the lone pairs, and it's going to do a substitution at the alpha carbon. So that X group, that's the leaving group, that leaves, and it's been substituted by the nucleophile. So alternatively, in our interpretation of the reaction conditions, is the thing in there going to be a base? So what we'll learn today, a base also supplies a pair of electrons, but its action is to abstract a proton. And so that is going to happen from the beta carbon. So if you follow the red arrows, that beta CH bond gets deprotonated. Its electrons then collapse to form a pi bond, and then the leaving group leaves. So what we end up with is a pi bond, in this case an alkene. And as you'll subsequently see later next week, you can form alkynes as well. So what do you end up with? The conjugate acid of the base, and then your leaving group as well. So really, it's important for us when we're looking at our starting material or our substrate to identify the carbon bearing the leaving group. We call that the alpha carbon. Any other carbon bonded to that, we were referring to as the beta carbon. And then we have to classify the total number of beta hydrogens. And as we'll see when we look at the nature of these bases, which beta carbon is the base going to go after? So that's going to make a difference. The size of the base, the strength of the base, we'll discuss those factors as well. What's unique about this, we have a carbon that is sp3 hybridized. And we've seen from module 3 that those type of CH bonds have a pKa value of about 50. So they're very weak acids. However, when you have this situation of these 4 atoms, so H, beta carbon, alpha carbon, X group, that encourages deprotonation with weaker bases. So you can get away with using a weak base to abstract a weak acid. And the driving force for that is the formation of the pi bond. So to rationally understand and predict what products will be formed, we have to evaluate the beta hydrogens. So again, you need to know where the beta carbon is, look at the hydrogens, attach to them, count them, classify them. Are they methyls, methylenes, methynes, that sort of thing? So the question is, which hydrogen, so that's the main thing, which hydrogen will be deprotonated by the base? So it's not random. Again, it depends on the nature of the strength of the base, the size of the base, and the mechanism. Where do I have it here? Is going to use those 4 atoms that I mentioned, as well as the dihedral angle. So remember when we were looking at Newman projections, the relationship between 2 substituents. So in this case, we're looking at the H and X angular relationship. So that was the dihedral angle. For eliminations to happen, that angle must be 180 degrees. So the way I just drew it, like flat like that dihedral angle you would say is 0. So a better representation would be that. So the conformation of the molecule must achieve that H to X relationship, 180 degrees. And so typically we're going to use a Newman projection to figure that out. So why is this complicated? So if you imagine that that beta carbon has multiple hydrogens, when you do that rotation, it's going to put those other groups in different relationships. And so when you form the pi bond, you can have these substituents end up on the same side or different sides of the pi bond, and those are different compounds. So alkenes have cis and trans geometrical isomers. The way the mechanism works, preferentially through that 180 degree relationship, you look at those things, remember, like gauche relationships, what's the energy penalty? You figure out what's the minimum energy penalty, and that helps predict the major product. So let's start off with kind of review of things so we can see how this gets increasingly more complicated in evaluating the beta hydrogens, which one's going to get abstracted, and then what the major product will be. So if we start with butane, we're going to treat that with a molecular halogen in the presence of heat. And it says the product has mass spec data where the parent, so M, and then this, that's M plus 2. So notice 135.98 and then 137.98. The difference is 2, so that's M plus 2. Those are the abundances. So look at that ratio and then determine what halogen was used for X. Any ideas? So remember that the halogens, certain halogens have signatures in mass spec. So fluorine, which is 100% abundant, does not really have a unique signature. Iodine is essentially 100% abundant, but it will typically give a fragment that is M minus 127. So the parent losing the iodine has a daughter ion that's 127 mass units less. Chlorine has two isotopes, 35 and 37, that give a ratio of 3 to 1. And then bromine, 7981, gives a ratio of 1 to 1. So if F and I are out, which one better matches the abundances that you see? So it's going to be the bromine. So the product of this, remember bromine was selective. So it's going to do a CH substitution at the secondary position to install bromine there. And really what that means, why you're seeing two masses, so that was your M, that's your M plus 2. So the ratio of the M to M plus 2, that tells you that bromine was used. Now we have this molecule with an alpha carbon. So we're going to do the evaluation of the beta, then we're going to look at bases, and then do elimination. So what is the name of the major product? So it's going to be C. So we're starting with butane. It has to be a butane derivative. We've substituted at the 2 position, so it's 2-bromobutane. So D is not correct because remember, substituents have to get the lowest number on the chain that they can. So there's 2-bromobutane, there's the alpha carbon. How many beta carbons are there? So there's 2 beta carbons. So that's helping us funnel down into predicting the right answer here. So the beta carbons are at carbons 1 and 3. So we don't even have to worry about anything at carbon 4. So there's 2 beta carbons. How many total beta hydrogens are there?
5.
So there's 5. We have 3 there and 2 there. So now again, this is telling you you have a choice and you have to diagnose the reaction conditions to figure out where the abstraction is going to happen. This. Without even looking at the mechanism yet. If we do an elimination from the beta carbon with 3 hydrogens, what's the name of the product? So we're going to eliminate from here. So remember, an elimination forms a pi bond. So we don't even need to know the arrow pushing. We're just sticking a pi bond between carbons 1 and 2. So the name of that is now butene. What if we eliminate from the beta carbon with 2 hydrogens? We're now going to put the double bond between carbons 2 and 3. But notice the issue now. So these are both called 2-butene. The 2 tells you the start of the pi bond. And then we differentiate them by looking at the major substituents. So you have H and H, carbon and carbon. So carbon's going to take priority. They're both on the same side, so this is called cis-2-butene. The isomer on the bottom, those groups are on opposite sides, so that's called trans. There's also other terms that are used. So the letter Z is used for cis, and E is used for trans. E and Z are probably better descriptors, because as we'll see when we learn other reactions, cis and trans, it's a little bit more general, but cis and trans helps us describe the relationships on rings. Are they on the same face of the ring, or are they on opposite faces? So those are the products of elimination. We looked at the alpha carbon bearing the leaving group. We identified 2 beta carbons. Then we just stuck the pi bond from alpha to beta on both sides. So those are the 3 possible products. But again, as I mentioned, we want to figure out what would be, of those 3, what would be the major product. That's dependent upon the strength of the base, the size of the base. So, how do I want to phrase this? Maybe let me just go back. So to help us further understand that, let's dig a little bit deeper into the structural features of an alkene, really using the orbital description. So you know by now that looking at those carbon atoms, that each carbon is sp2 hybridized. So you have 3 hybrid sp2 bonds, and then the double bond is made up of the overlap of the p orbitals on each carbon. So as you see in these blue p orbitals, each carbon supplies 1 electron. They overlap. That forms the pi bond. That's what that second line means, the double bond. So we have a sigma bond, we have a pi bond. When we were talking about Newman projections and rotations, we know that sigma bonds can freely rotate. There's an energy penalty when you get to gauche or eclipsed interactions. When you put that second bond in there, that pi bond, that severely limits rotation, because now, you envision this as electron density above and below the sigma bond. So it's essentially locking in those carbon atoms so they cannot rotate. Now pay attention to the numbering on these substituents. So I'll say this blue carbon has substituents 1 and 2. The green carbon has 3 and 4. So 1 and 2, 3 and 4. On the left molecule, 1 and 3 are on the same side, 2 and 4 are on the same side. On the right, it's the opposite, 1 and 4, 2 and 3. That interconversion does not happen easily, because essentially what you have to do is break that pi bond, then it has to rotate and then reform. So the strength of the pi bond really does not allow rotation to happen. So those cis and trans isomers do not interconvert easily. You can make it do it, you just have to add energy in the form of heat or light. So the total pi bond, just to go through the table here, the sigma plus the pi bond is worth 611 kilojoules per mole. A sigma bond is worth 347. You subtract that from 611. That tells you the pi bond is worth 264 kilojoules per mole. So that would be the energy you have to overcome to convert cis to trans. So when we're evaluating those possible products, how can we help increase our confidence in determining which one's going to be the major one? And to predict that, we're going to look at the stability of alkenes. So alkene stability is determined experimentally through an addition reaction. So I'm just showing you a generic alkene. Those 4 bonds sprouting off, those can be hydrogens or different substituents. The addition reaction is called hydrogenation, so H2. So there's 2 hydrogens, there's 2 carbons. Each carbon atom is getting a hydrogen, so it gets reduced. So that's an addition reaction. So in the hydrogenation experiment, you can then measure the heat that is produced from that reaction. And then when you have a whole different library of alkenes, you just repeat this reaction for each, you measure the heat, and that's an indication of alkene stability. So the fallout of that is when you're looking at the 2 carbon atoms, you're going to count any substituents that are carbon. So if this is carbon, 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 and carbon, that would be called tetrasubstituted. If you have 3 carbons, one of them, the 4th thing is a hydrogen, that's now trisubstituted. Now with disubstituted, you can end up with a couple different scenarios. The 2 carbon substituents are on the 2 different carbons. Their relationship can be trans or cis. If the 2 carbon substituents are on the same carbon, that's called geminal. So you'd have carbon, carbon, and then this would be hydrogen, hydrogen. So geminal means same, they're bonded to the same carbon. And then lastly, you only have 1 carbon substituent, that's a monosubstituted alkene. So in general, the more carbon substituents you have, the more stable the alkene. So from the 2-bromobutane, the 3 possible products were those. We had 1-butene, cis-butene, and trans-butene. Now using that trend, which one of those alkenes is the most stable? So let me add some clues here. So this is monosubstituted. This is di, that's di. Furthermore, this is cis, and that's trans. So we look at the structures, we classify them. We can see that the di-substituted trans, that's the most stable. Then the monosubstituted would be the least stable. And we can therefore conclude that of that product distribution, the disubstituted trans should be the major product because it's the most stable one that can be formed. So here are some numbers for us. We're taking our general alkene. We have these R substituents. We're doing an addition reaction. So we're adding the elements of H2 across that pi bond. That generates an alkane plus the heat, and the heat is what we measure. So we have our different substitution patterns listed across that row. We have a library of alkenes. The double bond is hydrogenated, that forms the alkanes. And then there's the heat that's measured. Notice the nature of that arrow. So it says increasing alkene stability as we move from left to right. So the mono-substituted generates negative 126 kilojoules per mole. So again, when you see that negative number, if you had your hand on the flask, that's heat being produced, so your hand would feel warm. So negative 126 for the mono versus negative 111 for the tetra. Notice the tetrasubstituted is generating the least amount of heat. So that means the alkene is the most stable. So again, if you're starting from 0, in this case, think of yourself as drilling down because heat is being released. You hit negative 111 before you hit negative 126. So whatever number you hit first, that indicates stability. Any questions? So kind of already previewed this. So those are the names, those are the structures. There's a new one in here just to show you how it's classified. So that was mono, this was di-cis, this one is now geminal. So digeminal, and this was di-trans. So the di has to be more stable than the mono. Then of those three, the trans is the most stable. One way you can rationalize why trans is most stable, see in the cis, those methyl groups are close. They take up space, they're sort of banging into each other. That makes it less stable. And we'll also see why through a Newman projection. So it says in the elimination reaction of 2-bromobutane, which beta hydrogen will be abstracted to form the least stable alkene? So A, B, C, or D? What? So let's walk through the steps for this. That's the alpha carbon. So remember that the beta carbons are right next door. If we were to continue sort of identifying, it would be alpha, beta, and then gamma. So we don't even have to worry about HD because it's not on a beta carbon. We don't have to worry about HB because that's bonded to the alpha carbon. So A or C, which one leads to the least stable alkene? A. So it's going to be A. So one way you can think about that, remember when you eliminate, it's going from an alpha to a beta. So you can sort of lasso those out. you lasso them out, and you have to plunk the double bond where you took them from. So that's going to give you the mono-substituted alkene, 1-butene. So we already said HD is not a choice, HB is not a choice, HA went to the least stable, so HC has to go to the most stable. But notice on this beta carbon here that I've identified, the complicating factor now is it has 2 hydrogens, right? So with that HA, that was a methyl group with 3 hydrogens. It doesn't matter which one of those hydrogens gets abstracted, as long as you follow the 180-degree rule. No matter which one you abstract, it's always going to produce that. But now if we focus our eye on this beta carbon, it will matter which one of these hydrogens gets abstracted, because they're going to lead to the 2 different di-substituted 2 butenes. So it says which beta hydrogen will be abstracted to form the trans alkene. So remember now we're focusing on that 180-degree relationship. So if the bromine on carbon alpha is pointed out towards you, so I'll do a new, maybe I'll call these X and Y. The bromine's coming out of the plane. You have to abstract a hydrogen that's 180 degrees away from it. So would that be X or Y? So it's going to be HY. So bromine's out towards you, HY is behind you. And that nomenclature is telling you that relationship between the bromine and that hydrogen is 180 degrees. So we remove HY. That will give us the trans alkene. So it says the cis alkene. In the conformation that's shown, we already know that HY, when it's abstracted, is going to lead to the trans. The relationship between HX and bromine, they're both pointed out towards you. So their angle cannot be 180 degrees. So what you have to do is a bond rotation. You have to move HX 180 degrees to the bromine. When I rotate this bond, this methyl group has to move. So I'm going to rotate it 180 degrees so it remains in the plane. So when I do that, it's going to come down that way. And so that's then going to put HX in the proper relationship of 180 degrees. The consequence of that rotation is now these methyl groups are on the same side. And so when we do the elimination of H to Br, we're going to end up with this cis alkene. So that will be a little bit clearer to understand when we actually start looking at the Newman projections. Remember, we're looking down a sigma bond axis, we're doing rotations, then we can line those things up properly. That'll help tell you which hydrogen gets abstracted and how those other substituents end up. So here is the arrow pushing mechanism. So this is E2. E stands for elimination. The 2 stands for bimolecular. So bimolecular elimination in the rate determining step involves the action of the base abstracting a beta hydrogen. So I'll highlight that arrow in yellow. So those electrons are abstracting that hydrogen. The electrons in the CH bond are collapsing to form the pi bond. And then the leaving group leaves with its shared electrons from that covalent bond. In the center here is the transition state. So in that square bracket, that's showing you partial bond formation. So base abstracting proton. That existing bond is breaking. The new pi bond is making. The leaving group is breaking. And so as it's drawn, that would form the trans 2-butene. You end up with the conjugate acid of the sodium methoxide. So that's ethanol. Then you have this inorganic byproduct, sodium bromide, that contains the leaving group Br minus. So the important thing is that relationship. So as it's drawn, that's 180 degrees. So those 4 elements, H, carbon-carbon leaving group, must be 180 degrees. Another way that we phrase that is anti-elimination. So the H and the X group are anti, 180 degrees apart. So why is that 180 degrees so important? If we look a little bit closer at the nature of the orbitals involved, we have this carbon-bromine bond, so that's a sigma bond. But due to the conservation of orbitals, there has to be an anti-bonding orbital. And that's what's highlighted in this maroon color here. So the sigma is the bonding, the sigma star is the anti-bonding. Notice it's 180 degrees away from the bonding. And we use that to explain why an SN2 reaction has to approach opposite. We're also going to use it to help explain this relationship. There's the beta carbon, there's its hydrogen. Those are the electrons in that bond. So you have H carbon-carbon bromine, 180 degrees. These electrons are now properly aligned to flow into that sigma star orbital. So your base is abstracting. These electrons now go into that orbital. That leaves. So that forms your pi bond. So as I mentioned, everything that we learned prior, the acid base, the pKa scale, then we learned about bond rotations, Newman projections, all of that is sort of coalescing now to help us predict what the major product's going to be. So if you've watched Seinfeld, do you know who Newman is? So I think Newman was his neighbor, was a postman who annoyed Jerry Seinfeld, and he would say, "Hello, Newman." So we're revisiting the Newman projection so that we can properly predict that orbital alignment. So in the center here, when we look at those two conformations, so remember a conformation is a conformational isomer, which you've done a sigma bond rotation. And so now we're looking at we're looking down C3 to C2. So C2 is bearing the bromine. C3 is the beta carbon of those hydrogens we're interested in abstracting. And then there's the two main conformers where we have the hydrogen, front carbon, back carbon, bromine. In that 180-degree relationship. So there was one H. If we do a rotation, so I'll put a box around that. The circle H moves there, the box H moves up. Now that's a different conformer that achieves the 180-degree rotation. And what you want to pay attention to, see the methyl groups. Here they're on the same side. Their relationship is gauche, 60 degrees. When you eliminate, they end up on the same side. So what this Newman projection unfolds to be, because you're only showing two bonds sprouting off, is to assume that there's now a pi bond between the front and the back carbon. So that gives you your cis. The other one gives you your trans. And if you notice the arrows here, it says it's favoring this one. So you have two conformers. This is the more reactive conformer because the methyl groups are not incurring any of that strain from the gauche interaction. And so that's going to lead to the production of the trans isomer as the major product. Any questions? So now we get into a little bit more complicated reaction coordinate because you have your starting material that exists in two different conformers. So this was the one with the gauche relationship. This was the one with the anti-relationship of the methyl groups. They interconvert through an eclipsing interaction, so that's just the bond rotation. This one was more stable relative to that because of the gauche. When this does the elimination, it goes through the transition state, results in the production of the trans isomer. So notice that that trans is lower in energy than the cis. So what's complicated about that? You have to look at the molecule. You have to determine what are the possible conformers, then which one's the reactive conformer. So the more stable conformer is not always the reactive one. You have to examine all of them, see which one's the reactive one. Questions? So let's, we'll spice it up a little bit. And now we're going to constrain those 4 atoms, H carbon-carbon leaving group, into a ring. So there was a question about OTS on the exam. TS is an abbreviation for para-toluene sulfonyl. It makes that oxygen a good leaving group. So OTS, that's the leaving group on the alpha carbon. When we look at that ring, we can see there's a beta carbon, there's a beta carbon. So 2 beta carbons. How many hydrogens are on this beta carbon?
Which one?
Can you see the laser moving?
2.
So there's 2, and then this one has 1. So why are we looking at this? What's complicated about it? Remember that cyclohexane rings, even though it's drawn flat, they do not exist in a flat conformation. They're chairs, remember. So in the chair form, you look at a carbon, the substituent can be either axial, so straight up or down, or equatorial. It's at an angle along the equator of the molecule. So why is this more complicated? Remember, you have to have the H in the leaving group 180 degrees. So it depends on having those substituents in the proper disposition. So we're going to look at unfolding the flat cyclohexane into the chair form, then evaluating, are those hydrogens axial or equatorial? So OTS was bonded to the alpha carbon. We said there was beta and beta, so 2 beta carbons we have to consider. So in your mental processing unit here, can you convert the flat cyclohexane into a chair? So let's take a step back. Can you eliminate one of them?
B.
Why are we eliminating B?
2 carbons away.
So the tosyl group and the methyl group, that's a 1-2 relationship. In B, it's 1, 2, 3. So we can eliminate B. Now A, C, and D meet the requirement of the 1-2 relationship, but now we have to consider the tosyl group is down, the methyl group is up. So remember when I talked about cis and trans? We would say that that relationship is trans. They're on opposite sides of the ring. So you initially said C, right? So what's the issue with C using that description? So they're both up. So that's why C can't be correct. And then between A and D, can we eliminate another one? So we can eliminate A because then they're both down. So D is the correct answer. So that's down. And the methyl group is up. So that helps explain sort of what face. But then there's also these other descriptors. Looking at the carbon bearing the tosyl group, is the tosyl group axial or equatorial?
Could you repeat that question?
The O-tosyl group, is that axial or equatorial? So it's equatorial. So we'll get to these next questions in the next couple of slides, but what I want to do is I want to redraw that chair. So now I'm going to put in those beta hydrogens. So that's the alpha carbon. We don't have to worry about its hydrogen. There's beta. There's the other beta. Remember we said the relationship between the beta hydrogens in the leaving group has to be 180 degrees. In this chair form, that requirement is not met by any of those hydrogens. So I'll leave it to you to prove to yourself through drawing some Newman projections of that that's not feasible in this chair conformation. So this H carbon-carbon tosyl, that's not 180 degrees. This H carbon-carbon tosyl, that's also not 180 degrees. This H carbon-carbon tosyl, it's not 180 degrees. So this is what we were just looking at was A. And then the B conformer is when we do the chair flip. So we're essentially flipping this carbon down, flipping this carbon up. So remember that with any chair, there can be two conformers, the two chair flip conformers. It says of these, which one is the most stable? Do you remember with evaluating chairs, how we evaluate stability? We want the substituents to be what? I think I heard it. Equatorial. You want as many equatorial substituents as you can get. So with A, they're both equatorial. That's the most stable, right? But we also said it's also not the reactive conformer for E2. However, when we do the chair flip to B, let's draw the hydrogens in now. So that's your alpha carbon. We don't have to worry about that hydrogen. We have beta and then beta. So I'm going to redraw that a little bit bigger. So I've identified in blue the three beta hydrogens, A, B, and C. Now, when you look at that conformer, which is the least stable conformer because you have axial substituents, do any of those hydrogens, A, B, or C, meet the requirement of 180 degrees away from the Tosyl group? So HB. HB is axial. The Tosyl group is axial. So HB, carbon, carbon, Tosyl, that relationship is 180 degrees. So now imagine eliminating across there. That looks a little funky. Notice those two remaining hydrogens on the double bond, they have to be cis. In a six-membered ring, you cannot have a trans alkene. So that's equivalent to this. So the fallout of this analysis, we identified 3 beta hydrogens. We had to look at the 2 conformers. We saw one was more stable, but it was not reactive. So we had to do the chair flip. That got us the reactive conformer. And it's telling us that this specific hydrogen is the only one that can get abstracted because that meets the angular requirement for elimination. So that plunks the double bond at this position. If we count those substituents, we see there's 1, 2, so that's a di-substituted alkene. If it were feasible to eliminate HA, what class of alkene would you get? Tetra, tri, di, mono? So you're going to put the double bond between this carbon and that carbon. So even though it in theory could be possible to form a tri-substituted alkene, which is more stable than di, you can't form it because the mechanism does not allow it due to the angular dependence. So again, these are part of the complicating factors in understanding and predicting as we move forward. Even though you're evaluating the products across a trend of stability, you still have to follow the requirements of the mechanism. So this was most stable. This was least stable. This was not reactive. This was reactive. So B is the reactive conformation. And again, the molecule is flipping back and forth between these. So even though this one is, say, there in 80% of the time, it flips over to this, say, 20% of the time. When it gets to that, then it can get funneled towards the product. So as the concentration of that sort of decreases, more of this flips over to form. Eventually, you'll convert all of your starting material into that major product. So I'll do some highlighting here in red. So with these 6-membered chairs, the take-home message is H and leaving group must be axial. So that allows for your 180-degree relationship. And then again, I would definitely encourage you, whether you can sort of do it visually or if you break out your model kit, sort of put your eyeball right here and look down that bond, and you'll see the H and the Tosyl group have a 180-degree relationship. This H right here, that Tosyl, they're going to be 60 degrees, they'll be gauche. If you look the other way from this H to that Tosyl, that's also 60 degrees, that's gauche. And again, you're just following the rules of what the mechanism proceeds by. So what is the alkene product? Again, when I write these questions, I sort of write them in the spirit of how you see them on the final exam. Your final exams through the ACS are written by a committee of faculty throughout the entire United States. They get about 20 faculty that teach organic chemistry together. It takes about 3 years to write these exams. They go through a couple hundred questions. They narrow it down to 70. The theme of these questions is there's always like 2 very wrong answers. So when you look at this question, it says you're doing an elimination. The leaving group has to be gone. So B and D have to be incorrect. So those are your derailers. Then between A and C, that's where you have to apply all the logic that you've learned. And we saw that from that, we're going to form the di-substituted over the tri. And again, the minutia of evaluating A versus C, you can't get caught up in that stability trend, because if that's the only thing you remember, you're going to pick C. But the mechanism does not allow for that. It has to be A. So I think we only have about 2 or 3 minutes left. I'll stop here for today, but where we're going with, we're going to dig now deeper into the nature of the bases. So we'll look at oxygen bases, nitrogen bases, the pKa's of the conjugate acids, but also their size. Because when you look at the beta carbons, they have a certain accessibility. You look at the size of the base, which one matches better. That also helps predict the major product.